Hello students, welcome to the second session on root locus. In the last video, we have seen the stability concept and angle and magnitude conditions. And we have also seen the definition of root locus, which is the root locus is the path traced by poles of a transfer function of a system. And we have also seen that the open loop transfer function, that is g of s into h of s, will satisfy angle and magnitude condition. This gives us an information that the information on g of s into h of s, that is open loop transfer function, is enough to understand the behavior of poles. This implies that if g of s into h of s is given, we can draw the root locus. That means we don't need the complete information on the transfer function of the system, the entire transfer function of the system. We just need the open loop transfer function g of s into h of s. In this video, let us see the constructional steps for root locus with some examples. So to start with, given a g of s into h of s, step 0. So I named it as step 0 basically because it is not a step. You can say it is a property of root locus. It says that root locus is symmetric about a real axis. That means the structure of root locus above the real axis is a mirror image of what lies below the real axis. This is basically because the poles of the system can be of two types. Either they can be real or complex. So when they are complex, they always come in complex conjugates. That means, take an example as 2 plus or minus 4j. So 2 plus 4j above the real axis and 2 minus 4j below the real axis. That means whatever comes above the real axis, its replica will be there below the real axis. This is why we get root locus symmetric about real axis. So next step is to find out poles, zeros and branches. So it says if you have to first locate open loop poles and open loop zeros in S-planes. So what are open loop poles? Now we know that poles are the roots of the denominator polynomial of a transfer functions. Now as we are dealing with open loop transfer function, the poles are nothing but the roots of the denominator polynomial of open loop transfer function. Therefore they are called open loop poles. In the same way, the roots of numerator polynomial of g of s into h of s are called open loop zeros. Now we'll consider p to be the number of open loop poles and z to be the number of open loop zeros. Now there are two cases in this. Suppose p is greater than z. That means the number of poles of the system are more than the number of zeros. The number of branches of the system would be equal to the maximum of these two, either p or z. So as we have taken p is greater than z, therefore the number of branches will be equal to p. Okay. Out of these, z number of branches will start from poles and terminate at zeros. Here it is. And the remaining p minus z branches will start from poles and approach to infinity. Now we'll take another example or another case where z is greater than p. Here the number of zeros are more than number of poles. Again, the number of branches is always equal to maximum of p and z, whichever is maximum. If the number of poles are more, then those many number of branches. If the number of zeros are more, those many number of branches. Suppose z is greater than p, the number of branches is obviously z. So in this, p number of branches will start from poles and terminate at zeros, and the remaining z minus p number of branches will start from infinity and terminate at zeros. So from these two statements, one thing is clear. That means, so here is a note, branches will always start from open loop poles and terminate at open loop zeros. So you can remember this, p to z, branches from p to z. Now to understand this concept better, let's take an example. Suppose there are 5 poles and 3 zeros. That means P is equal to 5 and Z equal to 3. So I name those poles, that 5 poles, as P1, P2, P3, P4, P5, and I name the zeros as Z1, Z2, Z3, Z4, Z5. I'm sorry, here the alignment is missing. Actually, these arrows are starting from poles. From each pole there is an arrow downwards. Okay. So the fact says that, or the property says that, branches will always start from pole to 0. So as there are 5 branches, suppose there are 3 branches which will start from poles and terminate at 0. Now there are 2 more poles which are left unattended. That means I need 2 more zeros to terminate at, but I don't have it. Now what do is I fill this up with infinity. So this means out of 5 branches, 3 branches will start from poles and terminate at zeros, and remaining 2 branches will start from poles and approach to infinity. So let us take another example where there are 2 poles and 6 zeros. Now again the poles are P1, P2 and zeros are Z1 to Z6. So maximum is 6, therefore there are 6 number of branches. So one goes from P1 to Z1, another goes from P2 to Z2. Now for other 4 branches I don't have an initial point. Again I'll fill it up with infinity. So that means the 2 branches will start from poles and terminate at zeros, and the remaining 4 branches will start from infinity and terminate at zeros. Now we shall take an example. Now what we are going to do is, instead of learning through all the steps theoretical part at once, we shall take an example and work out each of those steps with respect to this example. So all throughout I have taken this example where I have a unity feedback system where G of S is K divided by S into S plus 1 into S plus 2, and it is unity feedback system, so H of S is 1. So my open loop transfer function is G of S into H of S as like this. Now what does the first step say? That I need to first mark the open loop poles and open loop zeros. So as the numerator does not contain any S term, there are no zeros, and the denominator is S into S plus 1 into S plus 2. So clearly there are 3 poles, one at 0, one at minus 1 and one at minus 2. I think you already know the poles are always represented by a cross mark in S plane. So these poles are marked in the S domain. Now as it says, P is the number of poles, that is 3, and Z is the number of zeros, that is 0. The number of branches would be the maximum of these two, which is 3. The next step is to see how many branches and how they are terminating. Like there are 3 poles, P1, P2, P3, and there are no zeros to terminate at. So I fill the gap with infinity. So this shows that there are 3 branches, all starting from poles, and they are approaching to infinity. Now this is step 2, to identify RL and NRL. RL means root locus and NRL is non-root locus. So this is to identify which part of the real axis is also a part of root locus. That means which part of a real axis also lies on root locus. Now to understand this, so take the graph where the poles and zeros are marked. So in this particular example, there are only poles which are marked at 0, minus 1 and minus 2. Now let us take an arbitrary point P1 . So I'm taking this arbitrary point P1 on different parts of real axis. So I'll take start from the rightmost section where P1. So before that, sorry. So before that, read this statement. A point on real axis lies on root locus if there are odd number of poles plus zeros to its right. Okay, to understand this concept better, let us see with an example. So I'm taking the same example where I'm marking an arbitrary point P1 on the right hand side of the real axis. Now what does the rule says? To its right, how many, first I need to check when I select a point, I need to check how many poles or zeros are there to its right. So in this case for P1 there are no poles or no zeros to its right. So the number of poles plus zeros is 0. So the thing is here the number of poles plus zeros has to be odd to make it as RL. So in this case there are no poles or zeros, therefore this entire section of real axis will not be on RL. That means it is NRL. Clear? Okay, next. Now as the next, I'll select an arbitrary point in the next section. So previously we have seen this part is not a NRL. So it is not a root locus, that is it is NRL. Now I'll consider the section between 0 and -1. I can choose any point in between. So I choose arbitrary point P2. To the right of it, when I'm seeing to the right of it, I see only one pole. So I see only one pole which is odd. So when it is odd, that section of real axis will be RL. So this section between 0 and -1 is RL. So in the next, I'll choose another section between -1 and -2. So for this point P3, to its right, see how many poles and zeros are there. So always remember poles and zeros together. We need to consider both poles and zeros. Suppose there is one zero here, I should consider that as well. So in this case it is not there. So there are two poles to its right. 2 is even. So it is NRL. So next I consider another point in the remaining section of real axis. So again, to this point, to its right, there are 3 poles. So 3 is odd. So whenever it is odd number of poles to its poles and zeros together to its right, then it is RL. So that means this part of the real axis is RL, and we have also seen this part is RL, and this part is NRL, and this part is NRL. So as a next step, so one more thing to note here is the complex conjugate poles. Suppose here in this case we have taken all our real poles. In case there are complex conjugate poles, then we need not consider them. Why? Because consider a point complex conjugate points. Suppose there are complex conjugate points here, one above and one below the real axis. So for the same P4, to the right of it, there are 3 poles. So if you consider these complex conjugate poles also, there will be 5 poles. So 3 is also odd, 5 is also odd. So it doesn't make a difference for being an RL or NRL. So what does this note says? You need not consider complex conjugate poles when you are deciding RL and NRL. You can just ignore them. So here we can mark the RL, NRL, and here in the graph. So the next point or the next step is about asymptotes. Now what are asymptotes? Asymptotes are the angle or the direction at which the branches are going to infinity. So we have seen that there are 3 poles and no zeros, therefore there are 3 branches going to infinity. Now when they are going to infinity, when they are approaching infinity, in which direction they are approaching infinity will be, that information is given by asymptotes. Now how do we calculate, or how do we come to know about asymptotes? P minus z branches approach to infinity along the asymptotes. That means here the number of asymptotes is equal to the number of branches that they are starting from infinity or they are approaching to infinity. So the number of infinity you see here will tell us the number of asymptotes. Now we need to calculate the angle of asymptotes. The formula for angle of asymptotes is given here. It is 180 degree into bracket 2q plus 1 divided by mod of p minus z, where q ranges from 0, 1, 2, 3 up to p minus z minus 1. So to make it simple, now when I consider this example, I have 3 branches going to infinity, therefore 3 asymptotes. So when I substitute in this, 1 plus or minus 180 degree, 2q plus 1. Now the values of q to be substituted are 0, 1, 2. Why? Because we have 3 asymptotes, you substitute 3 values. If there are 4 asymptotes, you substitute 0, 1, 2, 3. If there are only 2 asymptotes, you just substitute q equal to 0 and 1. That's it. And in the denominator, we have p minus z. Now when I substitute q equal to 0, I get 60 degree. When I substitute q equal to 1, I get 180 degree. When I substitute q equal to 2, I get 300. So if you notice a fact that when you see this, equation, you can see that it is dependent on p minus z, which is nothing but the number of asymptotes. That means doesn't matter what are your poles, where are your poles, where are your zeros, the angle of asymptotes is dependent only on p minus z, which is nothing but it is dependent only on the number of asymptotes. So this will help us to understand something more. So it is there in the next slide. So this table gives when the number of asymptote is 1, then the value of q to be substituted is 0, and p in place of p minus z you substitute 1 in case 1, and I get an angle as 180 degree. So when you look at the second row, when there are 2 asymptotes, p minus z is 2, substitute the value of q as 0 and 1. So I get the values of angles of asymptotes as 90 and 270 degree. So 270 degree is nothing but minus 90 degree. So the angle of asymptotes are plus or minus 90 degree. So in the same way, this table gives what are the angles of asymptotes based on the number of asymptotes, that is p minus z. So this is a simplified version. So this if you can remember this, you can move ahead of a step in a faster way. Next step is to find the centroid. Centroid is a point of intersection of asymptotes on real axis. So notice that it is a point on real axis. Now how do we calculate a centroid? Summation of poles minus summation of zeros divided by p minus z. This formula gives the calculation for centroid. I repeat, summation of poles minus summation of zeros divided by p minus z. So summation of poles is nothing but summation of values of all the poles, and summation of zeros, it is addition of or sum of all the zeros, divided by p is nothing but the number of poles and z is number of zeros. Now when I consider the example which we have taken up, I have 3 poles where p equal to 3 and z equal to 0, and they have 3 poles. The values are 0, -1 and -2. When I substitute in the formula, I get centroid as -1. Now, so far what we have seen, we identified what are the open loop poles, open loop zeros. We identified number of branches, and among them how many are going to infinity. So the number of asymptotes is equal to the number of branches going to infinity. Then we learned the angles of asymptotes and centroid. So let us mark all of these on the graph. So centroid is at -1 here, and there are 3 poles, and the angles of asymptotes are marked +60, -60 and 180 degree. And this is the point, the centroid is a point where these asymptotes will intersect. So that means I should draw the angular lines from the centroid. Here is an important note to remember. Centroid may or may not be on root locus. This is very important. In this case, it is lying on the root locus. The centroid value may not be on the root locus as well. So the next step is to find out breakaway or break-in point. So breakaway or break-in point is the point at which the multiple branches will meet and depart. So in general, usually we don't differentiate between breakaway or break-in point, because as far as drawing of root locus is concerned, or calculation of breakaway and break-in point is concerned, it is all same for both breakaway and break-in. So in general, we call it as breakaway point itself. Now to identify the breakaway and break-in points, we have some prediction rules. Okay, so we need to first predict where can be the breakaway point in S-plane. So read this carefully, that if there are 2 adjacent poles on real axis and the section between them is RL, then there exists at least one breakaway point between them. So this means, suppose on RL I have two poles, adjacent poles, and in between whatever I have, this section is RL. Then I get there is all the chance that there will be at least one breakaway point in between them. Anywhere in this section there can be a breakaway point. So that is one prediction which you can do. Okay, next, this says, if there are 2 adjacent zeros on real axis and the section between them is RL, then there exists at least one break-in point between them. So for example, suppose on a real axis you have 2 adjacent zeros and the section between them is RL, then in between this section, between these 2 zeros, there is a possibility that there will exist a break-in point. Next, if there is a 0 on real axis and to the left of which there are no poles or zeros, and the part of the real axis on its left is RL, then there exists a break-in point on that RL. To understand this better, suppose this is a real axis. So I have some poles or some zeros here. And suppose I have a 0 as a leftmost thing, and to the left of which whatever section of real axis I have is RL, then there exists one breakaway, or what we call it as break-in point. Okay, so we can understand this better when we look into an example. Now here is a note breakaway or break-in point always lie on root locus. So in the previous case we had centroid which may or may not lie on root locus, but a breakaway point always lie on root locus. Now to determine the prediction is just gives an idea where the breakaway point can be. Now there are steps to be followed to really calculate the exact value of breakaway point. Now here are the steps. Predict the presence that we have already seen. First predict where can be the breakaway point. Then construct the characteristic equation. Then get an expression for k. First get the characteristic equation 1 plus g of s into h of s equal to 0. Then rearrange the terms so that you get an equation like k equal to the other terms. Then differentiate that with respect to s, that is differentiate k with respect to s where you get dk by ds, and equate that to 0 which you get an equation, and find out the roots of that. Find out the roots of dk by ds. Now you will get some values for s. Obviously dk by ds will be in terms of s. So the roots of s, roots of that equation would be some values for s. Now suppose I get s equal to 0, 1, 2. Then the next step says substitute the value of breakaway point in expression for k. Here you would have got the expression for k equal to something, some function of s you would have got. Now substitute these values of s whatever you have got in this expression. Then you get a value of k in this. So if k is valid, then it is, that is when k is positive, it is a valid k. We have already seen that k always varies from 0 to infinity. Therefore, when you substitute the value of s back into the equation of k, and if you get a positive value of k, that means it is a valid breakaway point. So if you get a value of k negative or even it is 0, then it is an invalid breakaway point. Now let us do the same procedure with this example. We have g of s into h of s given. Now first step is to construct. So before that we need to see or predict. So we already know, we have seen that it has three poles, 0, -1 and -2. Now what are the rules says if there are two adjacent poles? Now we have already seen, I'll take a different color to mark RL. Now we have already seen this part of the real axis is RL and this part of the real axis is RL. Now what is the prediction rule says? If there are two adjacent poles, I'm considering these two adjacent poles, and section between them is RL, then there is a possibility of having a breakaway point in this section. So I draw it again. That means we have seen that in this section there is a possibility of breakaway point. Now we'll see the same rule can be applied here. There are two adjacent poles here and the section between them is NRL. So the prediction says if the section between them is RL, then only there is a possibility of breakaway point. So there is no possibility in this section. The other rule says that adjacent zeros. Anyway, in this case it is not suitable. And the third rule says, just to recall you again, we'll go to that slide. The first rule talks about adjacent poles and in between them is RL, then there is a possibility. The next rule says adjacent zeros, and the next rule says the leftmost zeros. Anyway, these two rules are not applicable. So this rule is applicable, and we have predicted that there might be, so we can see in this graph that there might be a possibility of a breakaway point in between this section. So resuming to the previous slide, here g of s into h of s is given. Construct the characteristic equation, that is 1 plus g of s into h of s equal to 0. Simplify that and I get a characteristic equation like this. The next step says get an equation for k. So bring other terms here. So k, I get it as minus of s cube plus 3s square plus 2s. Next step is to differentiate with respect to s. So in this case, differentiate k with respect to s, that is find out dk by ds, and equate that to 0 to get the roots. As this is a quadratic equation, I get to 2 roots. That means the roots of this dk by ds equal to 0 will give a possible values of breakaway point. So that means the breakaway point can be either minus 0.422 or minus 1.577. So if you remember, when we had predicted we have a pole here, we have a pole here at 0, minus 1 and minus 2, and we predicted that there might be a breakaway point in the section between 0 and minus 1. So this 0.422 will lie between this section. So let me draw again. Now this point minus 0.422 lies in this section, and minus 1.577 lies in this section, and as per our prediction, one breakaway point exists between 0 and minus 1. So clearly you can identify that the minus 0.422 is a valid breakaway point, but to ensure that, it is always good to go with the calculations. So what does the step says? The last step says that substitute the values, whatever you had got, values of s, into the expression for k. What do I do is substitute the value of s equal to minus 0.422 into the expression for k. Substitute the value of s and get the value of k. So where you have got k equal to 0.3849, which is positive. This tells that this value of s is a valid breakaway point. In the same way, you can substitute s equal to minus 1.5774. I get a k value as negative, which says this is an invalid breakaway point. Now mark this breakaway point in the s domain, which is minus 0.4226. This is the valid breakaway point. Note the fact that so see the note that breakaway point always lie on root locus. So the next step, it is the point of intersection of root locus with imaginary axis. That means where at what point does the root locus crosses the imaginary axis, that is y-axis. Now here are the steps. Quickly let us go through. The first step is characteristic equation. Construct the characteristic equation. Second step says construct the roots array. You would have already studied that how to construct a roots array, how to find a marginal value of k, which is root RH criteria is another way of analyzing the stability of a system. So from that you already know how to construct a roots array. Then find the marginal value of k. So how do you calculate the marginal value of k? So we make entire row of a roots array 0 except s raised to 0 row. Then the row above that would be an auxiliary equation, which we get it as a of s equal to 0. So in a of s equal to 0, substitute the value of k as k marginal. Whatever you get from the previous step, k marginal value, substitute in this a of s equation. And the roots of this auxiliary equation are nothing but the points of intersection of root locus with imaginary axis. So one thing you can see from here is it is a point on imaginary axis. That means the points of intersection will always come as pairs of purely imaginary terms. That means this is an S-plane, so this is imaginary axis. If there is a point of intersection of root locus on the imaginary axis, there should be its complex conjugate. So always the values of points of intersection should be something like plus or minus j omega. Now we shall see the example where g of s into h of s is same. Now construct the characteristic equation. So here we have constructed. So this is the characteristic equation. So this we had constructed already from the previous step as well. So you can straight away take this. Then construct a roots array from the coefficients of this characteristic equation where they are 1, 3, 2 and k. Now we get this next term as 6 minus k divided by 3. So if you don't know, if you have forgotten, please go back and see how to construct roots array. So this is the row of 0. Now equate this to this term to 0 to get the value of marginal value of k. So you can see in this 6 minus k divided by 3 is equated to 0, where you get k value as 6, which is nothing but the marginal value of k. The next step says to construct the auxiliary equation. Auxiliary equation is constructed from the row above the 0 row with 3s square plus k. 3s square plus k equal to 0. Substitute the k value as 6, which is a marginal value. So here you get s square as minus 2, where the roots would be plus or minus j root 2. So as I said, point of intersection of root locus with imaginary axis will always be in the form of plus or minus j and some number. Now here you can observe the fourth point here says that construct the auxiliary equation with a positive value of k marginal. What if you get a negative value for k marginal? So as you know already, k is a system gain and that should be always varied from 0 to infinity. Suppose you get a k value negative, that means it is invalid. So which tells you that the root locus will not intersect with the imaginary axis. Now we are coming to an end, almost towards an end, which is not we are left with one more step that we will see later. Now so far from the previous steps, what all we understood, we identified poles and zeros and we identified number of branches. So whatever information we have got from the previous steps, mark it on the S plane. So here you can see we have marked all the poles. We have also marked RL and NRL. We have also marked breakaway point, centroid, point of intersection. So plus or minus j root 2 is nothing but root 2 is 1.414. That is also marked on the imaginary axis. Plus j 1.414 and minus j 1.414. So this is all the information that we have got from all the previous steps. And we have to also mark the angle of asymptotes. Here they are marked. So the 3 asymptotes starting from the centroid minus 1. So the angles of asymptotes are 60 degree, minus 60 degree and 180 degree. So before actually going for drawing a root locus, first mark all the points. Now how do we draw the root locus? Now we are done with all the points. Now it is time to draw the root locus. Observe carefully that, so we have seen all the branches, there will be 3 branches, and all the branches will start from poles and they go to infinity. And in which direction they go to infinity? One will go in the direction of 60 degree, one goes in the direction of minus 60 degree because of this asymptotes. Another goes in the direction of 180 degree. So here in this you can see a branch starts from this pole, okay, and in which direction goes it goes. So it might go in the direction of 60, minus 60 or 180 degree. So as you can see, to the left of this pole, the part of the real axis is RL as well. It is very clear that the branch starting from the pole at minus 2 goes along the direction of 180 degree and it goes to infinity. So it is clear that one branch starts from minus 2 and goes to infinity towards minus infinity. Okay, now there are 2 more branches. You can see here. Now there are 2 more branches which are starting from the other 2 poles, and very clearly the section between them is RL. Therefore the one branch should be going in this direction, other branch from the 0 should be going in this direction. And what is breakaway point? It is a point where 2 branches meet and depart. So the branch coming from minus 1, another branch coming from 0 are meeting at this breakaway point and then depart. That means one goes up and one goes down. So one branch coming from minus 1 and departs, and one branch comes from 0, meet at the breakaway point and departs. One goes upwards, one goes downwards. Now again there is another information which we have, that is okay. So now we have understood that one branch comes this way, another branch comes this way, one goes up and one goes down. Now my drawing is not very clear, it is just a rough sketch. Now we have another information that these are the points of intersection of root locus with imaginary axis. That means the branches of root locus should cut this point. That means I can predict that this branch which is going up should definitely cut this point, and the other branch which is going down should definitely cut this branch. Now after it cuts the imaginary axis, where does it go? It obviously goes to infinity. In which direction it goes? The asymptotes will tell us in which direction they go. Now doing it again. One branch coming from this direction, cutting this imaginary axis, and it goes to infinity in the direction of one asymptote, that is at 60 degree. Another branch, I'll take a different color pen. Another branch starts from this, comes down, breaks away, comes down and cuts the imaginary axis and goes to infinity in the direction of minus 60 degree. And we, in the initial part itself, we have seen the very first branch which goes from the pole minus 2 and in the direction of 180 degree to the minus infinity. It goes to minus infinity. So this is how your root locus should look like. You can see the output from the clearer output in this. So this is how your root locus should look like. You can observe. So the three branches are colored in different colors, one in green, one in blue, and one in orange, which goes from -2 to infinity. Once we get the complete root locus, it is important to analyze the stability of the system. So from root locus, now you can observe that some part of root locus lies on the left hand side of S plane and some part lies on the right hand side of the S plane. The root locus, two of the branches of root locus will intersect with imaginary axis at 2 points that are plus or minus j 1.414. So if you remember, how did we obtain these points? Let us go back to that slide where we obtained. So here we first calculated k marginal and then we obtained the roots as plus or minus j root 2, which are nothing but root 2 is nothing but 1.414. That means the root locus intersects with imaginary axis at a marginal value of k, that is 6. At this point of intersection, k marginal was 6. That means if we increase the k marginal from value 0 to 6, the part of the root locus is on the left hand side of the S plane. Once the k value reaches 6, it intersects the imaginary axis, making the poles marginally stable. Then when k is increased beyond 6, the root locus goes into the positive side of the S plane, which makes the system unstable. So from this we understand that to make the system stable, we need to keep the value of k within 6. The moment it reaches 6, it becomes marginally stable. So to make the system stable, we should always keep the value for this particular system, the value of k in the range of 0 and less than 6. Now we are done with drawing the root locus for the system with open loop transfer function example which we had taken, that was k divided by s into s plus 1 into s plus 2. Now there is one more last step left. Angle of departure or arrival for complex poles and zeros. So one thing to note here is the angle of arrival or departure is applicable for complex poles or zeros. Now what is angle of departure? Angle of departure is the angle at which branch departs from a complex pole. Now the formula for that is phi d. It is phi d, phi suffix d is equal to 180 degree minus phi. So what is phi? It is not clear in this. So I'll read out for you where phi is. I'll read out this for you. Phi is summation phi p minus summation phi z. This is something like this. Phi is summation phi p minus summation phi z. Now what is summation phi p? Summation phi p is sum of angle contributions at the required pole by all other poles, and summation phi z is sum of angle contribution at the required pole by all other zeros. You can see a note, angle of departure is applicable for complex poles. You can understand this better when we take an example shortly. So in this, the angle of arrival is much similar to angle of departure with a very little difference. Angle of arrival is the angle at which a branch arrives at a zero, and that is phi a, which is 180 degree plus phi. So you have seen that in angle of departure we had 180 degree minus phi, and in this it is 180 degree plus phi. The definition of summation phi p and summation phi z will remain the same, but it is at the required 0 instead of required poles. In the previous slide you can see it is required pole because we calculate angle of departure for a pole, complex pole, and for angle of arrival it is required 0. That is, we calculate the angle of arrival at particular complex 0. Again the note says angle of arrival is applicable for complex zeros. Let's take an example. Suppose I have number of poles and zeros here, they are marked, and I want to calculate. So clearly you can see where are the complex poles. So this pole and this pole is complex. Rest all, so I name them as this is P1, this as P2, and this as P3. Okay, and this is my pole of interest where I want to calculate angle of departure. Angle of departure is for complex poles, angle of arrival is for complex zeros. Now as I have complex pole, I calculate angle of departure. Now I can name these as poles as P1, P2, P3, and there is only one zero which is Z1. Now what does the definition says? Angle of departure is 180 degree minus phi, and I need to calculate the angled contributions of theta P1, theta P2, theta P3. Now these are the angle contributions. So theta P1 is angle contribution by pole P1, theta P2 is angle contribution by pole P2, theta P3 is angle contribution by pole P3, and this is theta Z1 which is angle contribution by Z1. Now first step is I need to calculate all these angles, and this is another pole, we should not be missing this. This is theta P4, I can name it as P4, which is angle contribution by the other complex pole at my required pole. This becomes my required pole here. So this is my required pole at which I am calculating the angle of departure, and the way to find is connect all the other poles and zeros to the required pole. Then find out calculate the angles theta P1, theta P2, P3. So these those with suffix P are the angle contribution by poles, other poles other than this P, and theta Z is the angle contribution by other zeros. Now substitute in this equation. So in this equation, summation, first find out phi where it is summation phi p. Summation phi p is summation of all the angles contributions by other poles like theta P1, P2, P3 and P4, and phi z is summation of all the angle contributions by other zeros. We have only one zero in this example, so it is theta z1. So get the value of phi and substitute this back into this equation 180 degree minus phi to get the angle of departure. Read out a note here. Suppose for this P, the angle of departure, I get it as minus 58 degrees. Okay, for this P, suppose I get angle of departure as minus 58 degree. So you need not calculate the angle of departure for this complex pole separately. If it is minus 58 here it will be plus 58. Okay, so just the sign will reverse. Suppose it is 45 plus 45 degree here it will be minus 45 degree. Okay, this is what this note says. Let us get a more clear picture by taking one particular example. So for the previous example what we did, that is k divided by s into s plus 1 into s plus 2, that did not have any complex poles or complex zeros, therefore angle of arrival or departure is not applicable. So let us take another example In this case, this is only for calculation of angle of departure and angle of arrival. See that is the open loop transfer function is like this. Now get all the poles and zeros. Here they are marked. So there is only one zero, s plus 4 equal to 0. So s equal to minus 4. There is only one zero named as z1. There are two poles, real poles, as one at plus 1 and one at minus 6. And there are two complex conjugate poles, minus 2 plus 4j and minus 2 minus 4j. So as I said, always the complex poles will occur in conjugate pairs. So it is minus 2 plus or minus j. So I name these poles as P1, P2, P3 and P4. So as they are marked on the graph, and I name the Z as or 0 as Z1. Now I need to calculate the angle contributions. Now what is the step? First connect all the other. Now I need to I'm calculating the angle of departure at a complex conjugate pole, which is P2. Okay, so as I'm calculating the angle of departure at this particular pole, so connect this pole to all other poles and zeros in the system. So they are connected by the dotted lines here, and the angle made by them, it may not be clear. I'll read it out. So this is theta P1, this is theta P3 because it is P3, and this is theta P4. So the notation doesn't matter, it is up to you how you choose the notation. And this is the angle made by 0, therefore I name it as theta Z1. Now the important thing to learn in this is how to calculate the angle of, or these angles, theta P1, P2, P3, whatever we have. I'll tell you a simple step here. Theta P1. So theta P1 is nothing but it is angle made by the line which is connected between P2 and P1. So it is angle contribution at P2 by P1. So it is nothing but first subtract this. Always P2 comes first. Why? Because P2 is a pole, complex pole at which we are calculating the angle of departure. Therefore, subtract this P2 minus P1, substitute the values, you get a complex number. Find the angle for that. Here you can see this is P2 minus P1 is 4 plus J4. Convert it into R theta form, that is convert it into polar form. We'll get some magnitude with angle 45 degree. You can easily do it in your calc. So theta P1 is 45 degree. Next, theta P2. Sorry, P2 is not there because that is where we are calculating. So now it is theta P3. So P3, angle contribution by the pole P3 at P2 would be P2 minus P3. Remember, always P2 comes first because P2 is the pole where we are calculating the angle of departure. So P2 minus P3, substitute the values, get the angle. It is 90 degree. So you need not calculate this 90 degree because it is very clear. So this is when it is connected horizontally, with horizontal line, the angle made by this is clearly 90 degree. Okay, you need not calculate that, but even if you calculate, you will get it as 90 degree. Next is for P4, it is theta P4. So P2 minus P4 and get the angle, you get it as 186.87 degree. Next, all the poles are done. Next is 0, theta Z1. P2 minus Z1. P2 minus Z1, substitute the values, get the angle 63.43. So here we have got all the angles theta P1, P3 and P4, theta Z1. Now it is time to substitute them in the formula. First I need to calculate phi, summation phi p. It is angle contribution by all other poles, that is P1, P3 and P4. Substitute the values. Substitute with the values here, and this as a summation Z1. I get as phi as 198.44 degree. Now we have the angle of departure formula here. Substitute the phi value here. So I get angle of departure like this. This is minus 18.44 degrees. Now how do we mark? So this is how the root locus of the system looks like. So we have not done all the other calculations. So this we have taken up only for the calculation of angle of departure or arrival. So you can follow all the steps and see that you can verify that your root locus looks like this. The important thing here to note is angle of departure. Angle of departure is always with respect to horizontal line. So this is the point P2 what we had, that is pole P2, and we got it as minus 18.44 degree, which is marked here. That means the branch, this green branch what you are seeing, the green branch of the root locus what you are seeing is departing from the pole at an angle of minus 18.44. This is what the meaning of angle of departure. Now for another pole which is P3, which is complex conjugate, the angle would be the negative of what we had already got, which is plus 18.44. The branch, the red branch, is departing from this complex pole at an angle of plus 18.44 degrees. So that's all. Thank you.